So in this section, we're going to look at reaction mechanisms. And reaction mechanisms are extremely important when you get to organic chemistry, but here we're going to go over some basics of reaction mechanisms. So you remember from a few sections ago, we talked about how you can't use stoichiometric coefficients in order to draw conclusions about the rate order for a reaction. So for example, if you have two reactants, you can't assume that it's second order with respect to those reactants. And the reason for that is because we don't understand the mechanism of the reaction from the overall reaction. And here, what we're going to look at is how reaction mechanisms play a role in what's actually going on in terms of the rate of the reaction. So first of all, we have these things called elementary reactions. And elementary reactions, or steps in a mechanism, are essentially what species is actually bouncing into what other species in order to form product. And it doesn't always happen that way, okay? Because sometimes you have one thing that falls apart, so it doesn't even need to bounce into anything in order for it for the reaction to occur. So that is the molecular or the elementary reactions. And then there's the molecularity. So to talk about the molecularity, the most common ones are unimolecular and bimolecular. Termomolecular reactions do happen, but they're very rare. And at the very end of this discussion on the slide, I'll talk about that briefly. But here's a couple of examples of unimolecular reactions. Generally speaking, though, if we have A yields products, the rate equals Ka to the 1. Remember that this is an elementary reaction or a step in a mechanism. So therefore, this is actually what's happening. A is falling apart to form products. So here's an example. O3 falls apart to form O2 and O. Rate equals K concentration of O3. The more O3 you have, the faster the rate of the reaction. In this case, we have this hydrocarbon falling apart into two ethylene molecules. Okay, and in this case, the rate is equal to K times the concentration of this molecule right here. So these are unimolecular reactions. One thing falls apart into multiple things. In this case, they both fall apart into two things. They could fall apart into more things, of course. Bimolecular reactions. Bimolecular reactions can happen in two ways. Again, these are elementary reactions where these are the actual species that are reacting. So, or they're steps in a mechanism. So here we have A plus B yields products. In this case, A and B have to actually interact with each other and hit to form the product, presumably AB. Rate equals K, concentration A, concentration B. A to the 1, B to the 1. For elementary reactions, we can use the stoichiometric coefficients in the rate law because these are not overall reactions, they are elementary reactions. Sometimes they're both, but not always. In this case, we have two A's yields product. Sometimes A reacts with itself, or another A, okay, to form the products. In this case, the rate is Ka squared. Notice this stoichiometric coefficient becomes the order of the reaction. And here's an example. Two HIs in this elementary reaction actually bounce into each other. They form this transition state, and they form these products. So this is the mechanism of the reaction. These two form this transition state, which form these products. But it turns out that not all reactions work this way. Okay? Some reactions go through multiple steps. And when they go through multiple steps, things get a little bit more complicated. So here we have an overall reaction. NO2 gas plus CO gas yields CO2 gas plus NO gas. We cannot assume that the rate is K NO2 CO because we don't know for sure that these products are formed by NO2 hitting CO. So we need to investigate the reaction mechanism. And I am not going to talk about in this part of the course how one might investigate a reaction mechanism, but there are ways that are known to do these things. So in this case, what we find is the first thing that happens is NO2 interacts with NO2 to form NO3 and NO. And it turns out that the rate of this first step of the reaction is relatively slow compared to the second step. So once basically an oxygen was transferred, right? We had NO2, now we have NO3. We had NO2, now we have NO. Once its oxygen is transferred, NO3 interacts with CO to form your NO2 and your CO2. So although at the end of the day, we started with these two things and we ended up with these two things, this intermediate NO3 had to be formed in order to make this reaction occur. Okay, so now we have the mechanism of the reaction. Now, a couple things to note here. The first thing to note here is that the rate is dependent on the slow step. And that makes sense. Let's think about it in terms of a cattle example. If we wanted these cows to walk from here to over here in this pen, right, the distance between here and here, we could look at the rate at which cows walk, right? I don't know what the speed cows walk is or what this distance is, but they wouldn't be limited by anything, right? They would just walk. But here we have a limiting factor. And the limiting factor here is a gate. So the rate at which all these cows can go from this pen to this pen is affected by how fast each individual cow can make it through the gate. If you have a reaction mechanism, the rate of the reaction is dependent on the slow step. Whichever part is the slowest is going to depend on, is going to affect the rate of the reaction, right? You're not dependent on how fast cows can walk. If the cows just had to walk from here to here, that would be much faster than if each one had to go through the pen at any individual time. Therefore, the rate of the reaction, or the rate of this process, is not dependent on the speed of cows. It's dependent on the speed of going through the gate. Just like this reaction, the rate is dependent on the slow step and not the fast step. So, if we want to write the rate law, it would be rate equals K NO2 squared, because this is essentially two NO2s, right? So K NO2 squared. The rate of the reaction is dependent on the slow step of the reaction. The next thing that we want to look at is this in terms of a reaction coordinate diagram. So if we have a reaction coordinate diagram here, where this is our reactants and these are our products, we now have two humps, okay? Because this is a two-step mechanism. Couple things to notice about this. First thing to notice about this is, at the top of these humps, we still have the transition states. So there is some transition state where one NO2 and another NO2 interact with each other. That would be up here, okay, because it's the first step of the mechanism. And now there's some intermediates, okay? These are the intermediates of the reaction. The products of the first step of the reaction are the reaction intermediates. Sometimes you can actually stabilize reaction intermediates. You can't ever stabilize transition states. So we have some reaction intermediates. We then have another transition state where NO3 and CO are interacting with each other, and there's some transition state in between. And then we finally get to the products. If I did not give you this, and I just gave you this, and I asked you which is the slow step of the mechanism, okay, you should be able to tell me, or you would be able to tell me, it's the first step. How do I know that the first step is the slow step of the mechanism? The reason is because the activation energy of the first step is much higher than the activation energy of the second step. And as we talked about in the previous section, as activation energy increases, the rate of the reaction goes down. So the first step has a high activation energy, the second step has a lower activation energy, therefore the first step is the slow step. And the rate of the reaction is dependent on the first step of the mechanism. Take-home message from all of this. The overall reaction is not always an elementary reaction. Oftentimes, there are elementary reactions where these are the actual compounds that have to interact in between that add up to this overall reaction. We call these intermediate steps, or these elementary reactions, mechanisms, all right? So this is the mechanism of the reaction. This one has a two-step mechanism. Very often, there are different rates for the different steps of the mechanism. If the first step is the slow step, the rate is going to be dependent on whatever the reactants of the first step are. If the second step is a slow step, unfortunately, it's a little bit more complicated, and we will talk about that when as an example, because I think it'll be more helpful to see it as an example than me try to explain it with diagrams that are in my head and not on the piece of paper. So I'm going to switch back over, like usual, to the slide here. So here we have a reaction where the overall reaction is CO plus Cl2 yields CoCl2. And we have in this reaction, the first step, Cl2 forming 2Cl gas as a slow step. Then as the second step, we have CO and Cl form CoCl as fast step. And then we have CoCl reacting with the Cl to form the CoCl2, which is another fast step. So in this case, the slow step is the first step, the decomposition of the Cl2. We look at the reaction coordinate diagram, and you'll notice that the activation energy of the first step is higher than the second step, is higher than the third step. So the rate of this reaction is going to be dependent on getting over this first hump. Okay, I will note that I doctored this example a little bit for simplicity. So this is not 100% correct in case you were really caring about the rate of this reaction. So let's look at what's the rate going to be dependent on. Well, if I want to write the rate law, it's going to be rate equals K concentration of Cl2 to the 1 power, because the slow step, the only reactant is Cl2, and there's only one of them, so this is what the rate of the reaction is dependent on. Please note, that I did not use the overall reaction to do this. I looked for the slow step in the mechanism, and I used the slow step in the mechanism in order to write the rate law, because the mechanism has elementary reactions. These are the actual chemicals, the actual molecules that are interacting with each other. This is just what we would see happens, because we don't stop the reaction here and we don't stop the reaction here. We start here and we go all the way over to here. Okay? So, a couple other things to note. The transition states would fall here and here. Okay? And these transition states would be this product would be this transition state, and this product would be this transition state. The intermediates are somewhere where Cl is falling apart. Okay? Up here. Or where CO and Cl are interacting with each other somewhere up here. So this is basically how we could write the rate law for this given the mechanism or given the elementary reactions, kind of the same thing. All right, let's look at another example where we have the second step being the slow step. Unfortunately, when the second step is a slow step, it's a bit of a pain in the neck, okay? So in this case, the overall reaction is 2O3 form 3O2. And we have a mechanism, O3 falls apart to form O2 and O, and this is the fast step. So the activation energy here is this one. The second step of this reaction is that O3 plus O form O2, all right, which is the overall reaction, which gives us the overall reaction where O2 is the product. So that's this step here. And we have the transition state up here, and now we have the product. So we're saying that this is a slow step, or that this activation energy is higher than this activation energy, which they kind of look close on this graph, but this is the best one I could find. Okay, I should have made this more extreme so it's more obvious, but this is a slow step. All right, so let's take a look here at how we would do this. Well, your gut feeling is going to be that the rate equals K concentration O3 concentration O. So I'm going to write that down. Rate equals K concentration O3 concentration O. And this is exactly what I did in the previous question, right? I wrote the molecules interacting in the slow step of the reaction in the rate law. There's one O3, so it's to the 1. There's one O, so it's to the 1. And that's how I end up with this rate law. But there's a major problem with this rate law. And the major problem with this rate law is O is not in the reaction. So we can't have a intermediate in the rate law because it's not in the overall reaction. So we have to get rid of this. Now, how we get rid of this is a little bit of a, subtle trick. So the idea here is that if we have this intermediate it's actually going to be able to be more likely to fall back and form a reactant than to go over and form a product. Why is that? Because the activation energy to go backwards, okay, this much, is lower than the activation energy to go forward, this much. Said another way, this reactant and intermediate place reaches equilibrium before the molecules fall off and form, before the product is formed. Okay, the intermediate forms product. So this basically reaches equilibrium. So we have this direction, okay, being exactly the same rate as this direction. That's what equilibrium is. Believe it or not, the next 3 chapters are equilibrium. So we're getting a little bit of a chicken and an egg problem, which is a common problem in teaching chemistry. But this does reach this dynamic equilibrium. What's equal? Not the amount of this and the amount of these. What's equal is the rate of going in this direction and the rate of going in this direction. Because this hump is larger, or this has a higher activation energy, which makes this reaching equilibrium possible before this slow step occurs. So let's write the rate laws for the forward and the reverse reaction. So for the forward reaction, rate equals K1. I'm going to put the 1 at the bottom. Okay, K1 concentration of O3. All right. For the reverse reaction, going in this direction, so K is -1, rate equals K minus 1, concentration of O2, concentration of O. All right, so now I'm going to change this rate to a 2. All right, so I said this could be the rate law because we just took the slow step and wrote the concentrations of the 2 reactants, but I said you can't do that because this isn't in the overall reaction, so therefore we just changed this to K2. All right, so now we have these 3 reactions. We know that the overall rate is most dependent on this one, but we also know we got to get rid of that because it's not allowed to be in the mechanism, or it's not allowed to be in the rate law because it's not in the overall reaction. So here's what the math trick that we take advantage of. As I mentioned before, this is assumed to reach equilibrium. Said another way, the rate of the forward reaction and the rate of the reverse reaction become the same. Said another way, this rate and this rate are equal. Said a last way, K1 concentration O3 equals K minus 1 concentration O2 concentration O. So I just put these 2 things equal to each other because at equilibrium, the rate of this and the rate of this are equal. Now, what am I trying to get rid of? In this rate law, which is mostly good, what I want to get rid of is this. And what I want to replace it with is O3s and O2s. If you look here, we have this, and then we have O3s and O2s. So if I solve for concentration of O, then I can sub in here, and I'll only have O2s and O3s, and I'll have my rate law. So let's do that. We're going to divide by K minus 1, concentration O2. It cancels out. And we're going to divide by K minus 1, concentration of O2. And what we get, I'm just going to write the concentration O on the other side. Concentration of O equals K1, concentration of O3, over K minus 1, concentration of O2. Well, now I could plug this into here. All right, I can plug this in for this. Rate equals K2, concentration O3, times K1, concentration O3, divided by K minus 1, concentration of O2. Okay, now I'm going to move all the K's into the same area. So I'm just going to move these K's over. Rate equals K2, K1, divided by K minus 1, times concentration of O3, concentration O3, divided by concentration of O2. Like that. All right, so I just basically move these K's over here. Well, if we have a bunch of constants multiplied and divided by each other, it's still going to be a constant, right? A constant multiplied by a constant divided by a constant is still a constant. So rate equals some new k, all right, because that we're just simplifying this k. We have concentration of O3, and we have 2 of them, so squared, divided by concentration of O2. Now, if you were looking at this as a rate law, we'd probably just put this to the -1. So probably you would see it this way. Rate equals K, concentration O3 squared, concentration O2 to the -1 power. That's not clear. To the -1 power. Okay, that's not super clear, but that's basically that. I just took this and raised it to the -1 so I could multiply instead of divide, and I could write it in one line. So when the second step is the slow step, it's a bit of a challenge to determine the rate law, and that challenge is because we can't put reaction intermediates in the rate law, so we can't do it as simply as we did for the first step. For the case where the first step is the slow step, because the first step always involves molecules that are actually in the reaction, because you have to start with reactants. So the first step is always going to start with reactants.